Now we're going to summarize the behavior of the two MOSFETs that we just went over and how they relate to the input gate voltage. So we're given two different input voltages, a high and a low, and we're going to, in this chart, it summarizes what happens in the circuit when the different voltages are applied. So when PMOS has a high gate voltage, the channel is never generated, so that no current will flow. When the gate voltage is low, it will generate a channel across the gate and will allow current to flow. And it's just the opposite for NMOS. When the gate voltage is high, current will flow, and when the gate voltage is low, current will not flow. And these two states are what sort of allows digital circuits to take place. The fact that we can define each state as either high, low, on, off, and 1 and 0. Here's an example of a circuit with a PMOS transistor. We can clearly see that the gate voltage is directly connected to the independent voltage source. So we would consider this input high. And we just saw that when the input gate voltage is high, the PMOS is cut off. So this is essentially an open circuit at this junction, which means that no current will flow and the LED will not be on. In the opposite respect, we can see that now the input gate voltage is connected directly to ground. So this will be considered low. And we know that when the input gate voltage of a PMOS transistor is low, this transistor will create a channel across here, so essentially create a short. Current will flow through this resistor into the LED, and the LED will turn on. So now let's see another example with an NMOS transistor so we can see how exactly the states are formed. So let's say this is a voltage source equal to 5 volts in series with the resistor that's attached to the source of the NMOS transistor. And then we connect the drain directly to ground. And this is our input gate voltage. So let's consider the drain to source voltage, the output voltage here, V out. So if we were to draw a V out to V in curve, what would it look like? So we know our Vn is the same as our Vg. So when Vg is low or essentially 0, we know that for NMOS, the transistor will be cut off. Since it's cut off, there's no current flowing through the circuit, which means that V out will be connected directly to the source VDD, and the entire 5 volts will drop across it. So we have 5 volts across here. Now once Vn starts to increase, we already talked about how the channel starts to be able to form and then current is able to pass through. So when that happens, current starts to generate and then it starts to flow across this resistor. And we know back from Ohm's law that voltage through the resistor is directly proportional to current. So when there's current flowing through this resistor, there also will be a voltage drop across it that's directly proportional to the value of the resistor. Which means, since there's a voltage VR across here, we know that V out is going to be equal to the 5 volts minus the voltage drop across the resistor. So this will steadily drop off as current increases. The more current that flows, the more voltage drop across the resistor. So at some point, it will increase until the current saturates, no more current can be generated, and then it levels off at a certain value here. We'll just call it low. So we can see that in this cutoff region where the transistor is not conducting current, we see that we have the state that we can consider high. And then when in this region where the current saturates, we can consider this the low region at this point. This region in the middle is called the active region. Where actually it's in between the low state and the high state. So for digital logic and digital circuits, we don't want this active region at all. We want it to either be low or high. So essentially, we're unable to do that with a single transistor. So that introduces our next device called the Cmos transistor. The Cmos transistor is called a complementary metal oxide semiconductor, and it's essentially using an NMOS and a PMOS together in a cascode similar to something like this. Oh, darn. It's built in a cascode similar to something like this. By doing this, we know that either one of these two transistors will be on and the other will be off. So if this PMOS is on, we know that it's going to pull up V out to this voltage source. And if this NMOS is on, it will pull V out down to the ground. So if we draw the V out, V in characteristics of this, it looks more like a more steeper transition. This active region here is much steeper, and it will end up drawing the voltage, either pushing it high or forcing it to go low. The advantage of this is that it also draws very little current, which ultimately makes this transistor very energy efficient and very useful for digital circuits.